So I'm an architect, and I've been working the last 17 years on trying to think of our buildings and cities not as well-composed facades or like interesting sculptural volumes, but as man-made ecosystems where we think about how we channel not only the flow of people through our cities, but also the flow of resources. So really trying to not just draw floor plans, but actually also try to draw how our environment channels our resources. I'll start by just showing a few examples of some of the work we've been doing here on Earth. This is my office. It's a refurbished former Carlsberg factory where they used to make the least exciting part of the beer, the bottle cap. And I have obviously very committed colleagues, because like when you're trying to change things, passion is a major driving force. And I thought maybe in this audience I'd start by showing, we just finished this building in the hometown of Lego. It's the Lego house. It's essentially the home of the brick. And in a space full of scientists and engineers, there'll be a few of you that played with Lego when you were kids. The entire roof is an interconnected playground, open for everybody. So you don't need a ticket to go here. You can actually just hang out. It's this sort of extremely interactive environment. Underneath the 8 skylights of the 2x4, you have a gallery of the mastery of Lego. Then you can go through and explore different aspects of Lego. And finally, you can descend into the treasure chamber where the crown jewels are kept, including, I think, the most important Lego set ever made, the Yellow Castle from 1979. It was my own first Lego set. And of course, you can also get the Lego house. I think it's maybe the highest honor any architect can achieve is to be immortalized in Lego. Another example, I did a sports hall from my old high school. We buried it under the ground. And to not take more space than necessary, we based the curvature of the roof on the mathematical formula for a ballistic arch. So it's literally shaped by rocket science, if you like. We did the Danish pavilion in Shanghai about sustainable cities, where we celebrated, for instance, in Copenhagen, 40% of the Copenhageners commute by bicycle. So we made bicycle lanes so you could actually bicycle through the entire pavilion, making it the perfect museum for impatient people, because you could do the whole thing in 5 minutes. We converted a former dry dock where they used to build the ships into the Danish Maritime Museum. We just opened a museum on the west coast of Denmark in a nature reserve next to an old German bunker from the Second World War. But because you're not really supposed to build there, all we did was like cut a few slices into the dunes that then reveal as you go in these buildings that draw tons of daylight. Even though the whole museum is underground, it actually has an abundance of daylight, and you only see it as this sort of secret glow by night. We've done a handful of sort of multifamily homes, including a project we call The Mountain, that basically created a mountain of houses with gardens by putting them on top of a huge parking structure. You have a funicular elevator that gives access to all of the homes. We created a building called the 8 House, where you can actually walk and bicycle up this 3-dimensional community. So you literally have like almost small sort of scale community living in the middle of a 3-dimensional city block. And in the port of Amsterdam, we're building almost the inverse building. It's a city block on the waterfront where you can actually sail your ship into the courtyard as this sort of gateway to the port. In the port of Copenhagen, we just started our first, it's a project called Urban Rigger. It's using shipping containers to create floating student homes. 12 students live in one of these guys. They have like the most epic waterfront view. And a rent of $700 per month. And right next to it, we're building our biggest building in Copenhagen. It's a waste-to-energy power plant that is so clean that no toxins are coming out of the chimney. So we got the idea to turn the roof into an alpine skiing park. We have snow in Denmark, but we have absolutely no mountains. We have one now. This is a construction site photo. It opens in 1 year and could probably become like a landmark of Copenhagen going forward. In New York, we just finished a building called Via on the west side of Manhattan. It's basically taking the communal space of a courtyard and combining it, creating this oasis in the city, and combining it with the density of a skyscraper and creating this striking new landmark on the waterfront. And then finally, we're doing this park called the Dry Line, which is essentially the 10 miles of waterfront park designed in such a way that it combines the hard engineering that is necessary to resist an incoming flood with the social and environmental benefits of a rejuvenated waterfront. So in a way, you can see like all of the projects somehow deal with trying to solve more than just one problem with a solution. And that in many ways becomes relevant when you start looking at how you can turn Mars into a habitat for humans. Is it possible to dim these lights just a tiny bit for the image? And we got commissioned recently by the United Arab Emirates to try to see what it would look like to put an Emirate city on Mars by 2117. So it's not a super steep schedule. We have some time to think about it. But I mean, of course, you know, what's so compelling about Mars? So of course, like Mars is almost like the same size as some of the big moons of Jupiter. It's our immediate neighbor. It's not the closest neighbor, but it is one of our neighbors. And if you just compare to the other planets, Mercury is like burning hot, way too close to the sun. Venus is both toxic and hot. And then you have like the moons of Jupiter that are quite good, but they're six years away of a commute. So in that sense, Mars is a lot better. If you look at this sort of real estate evaluation, you can see Mars is performing quite well. It has a little bit too much radiation for humans, but it's actually fine for plants. And because of the constellation of the 2-year cycle of Mars and the 1-year cycle of Earth in big numbers, you actually have a good, every 2 years you have a window of opportunity where it could take between 3 and 6 months to get to Mars. Mars has roughly half the diameter of Earth, which gives it a 38% gravity, which is great for the architects because you can span a lot longer with the same materials. But it actually has the same surface area because it doesn't have any oceans. So there's a ton of real estate to find there. And then just like some of the coincidences that are amazing in a sort of cosmic scale is that Mars actually has almost the same 24-hour cycle as we do. It's like 40 minutes longer. So all biological species that have sort of originated accustomed to a 24-hour cycle are going to function fine on Mars. And then they have the same seasonal tilt as we do. So they have almost the same 4 seasons, which is also interesting. They don't have a liquid core, and they don't have a big magnetic field, which means that they are more exposed to radiation, as we also learned earlier today. And then just like a little experiential thing, the blue planet and the red planet actually flip during the sunset, because obviously our sunsets are red, but because of the fine-grained dust in the Martian atmosphere, blue light penetrates better than other colors, so you actually have blue sunsets, which is something we can hopefully all enjoy in the near future. And then also just, it's not so far off. There is a place on Earth, the Atacama Desert in Chile, which is the driest and most lifeless cold Arctic desert in the world, that actually has absolutely, there's been samples where they found absolutely no life, which is what we can probably expect on Mars. And Mars, we've actually been going there pretty consistently since the 60s, so we actually have really good knowledge, sort of evidence of frozen water, evidence of the dry ice of the 2 poles expanding and contracting, like different sort of land formation, dunes, mountain ridges, frozen lava flows, dunes that are sliding, a dried out archipelago, sort of a twister, a dust devil roaming around on the surface, and an active landslide happening in front of our cameras. And of course, with these little guys, 2 of them are still active, we have some good surface reconnaissance. So you can really start sort of imagining going and living here, and it doesn't look that different from New Mexico in some places. Obviously, a lot of great things. We get a lot of things for free. But we have these special challenges. Too much radiation for humans, very low pressure, very low temperatures, down to minus 150, no breathable air, and no sort of ready-to-use water. If we look at where we might go, it would be wise to stay within the 40 degrees of equator to have enough light for photovoltaics and have reasonably high temperatures. These are some of the landing sites that have been explored by SpaceX. These are some of the landing sites where we've already been. Also, an interesting sort of, the entire sort of northern hemisphere used to be an ocean, and the entire southern used to be dry land, which also means that you have very different surface textures. You can see you have way fewer impact craters, a much more even surface. So probably this like former coastline could be a good place to be. You also want to be relatively deep to have as dense atmosphere as possible to achieve the highest temperatures possible. This is Hellas Planitia, a 7-kilometer deep impact crater. Here you have some of these sort of old, dried-out riverbeds. And you have Valles Marineris, this like a huge Grand Canyon, 4,000 kilometers long, 7 kilometers deep. To begin with, we started sort of saying, where can we learn from Earth how one might inhabit? And just, if you look, this is like Tunisia. What looks like a lifeless desert is actually a sort of a densely populated village. Where the locals have developed these techniques of excavating homes into the soil to create more stable temperatures, protect them from the cold at night, protect them from the heat during the day, providing nice shade, but then still having like indirect daylight in their cozy interiors, protecting against the environment in one way. And another example, sort of almost referring to Valles Marineris, the canyon lands in Arizona, again, these like steep rock walls actually create these shelves where people have found ways to actually inhabit, protected from the elements by the rocks above them. Another sort of model that might be interesting on Mars. And finally, because like Mars is incredibly cold, if you look, this is Kangerlussuaq in Greenland, of course, where the typology of using the porosity of frozen ice as an insulator and using spherical forms to create the maximum protection from the elements in various materials. So one of the sort of thinking that has inspired us is Robert Zubrin in his book, The Case for Mars. He refers to Roald Amundsen, the guy who pioneered the Northwest Passage over Canada, by actually living off the land to living like a local. He learned from the Eskimo and the Inuit. So instead of like bringing big ships and horses and cars, he brought like kayaks and sleighs with dogs. And in a way, we have to become Martians if we want to succeed on Mars. So of course, like the first landers will have to bring everything they need from home, so it has to be like compact and light. Then maybe we can bring machinery to use local materials to create something, and eventually we can create a self-sustained ecosystem. So what we know that we have on Mars is regolith, some Martian sands, basalt, some meteorites. If we start by sort of sorting the regolith, we can extract probably some frozen water that we can keep, basalt stones, fine sands. We're going to use the water locally, but we'll also mix the water with the sand to create bricks, to create like ceramics or concrete. The fine sand, we should be able to sort it and find iron oxide and silicia, which we also know is there on the surface. We can use that to create glass and to make photovoltaics. The photovoltaics can drive an electrolysis plant where we can split the water molecules into hydrogen and oxygen. If we combine that with the CO2 heavy atmosphere of Mars, we can use the Sabatier reactor to create methane, and when essentially together with the oxygen can create rocket propellant. So we can come home and we can create like an air bridge or a space bridge between Mars and Earth. We can sort of we get water as a byproduct, and we get carbon monoxide that we can use with the iron oxide to create steel. We can use the carbon monoxide with the water in another chemical reaction to create different kinds of plastics, fiberglass, hard plastics, soft plastics, transparent plastics. Of course, we're going to use and recycle the plastics locally. We can also use it to create like transparent membranes we can use for inflatable habitats. Aquaponics, aeroponics will allow us to have a local production of food. Of course, recreation, environments, biophilia for the sort of psychological benefits of the humans, food production, and of course also root zones that are used to sort of clean the wastewater. So in a way, what we need to do is create a man-made ecosystem that can create a self-sustained habitat on Mars. If we look at how much space we need, in Western Europe, we have 150 square meters built per person. We imagine sort of on Mars, we could do with a little less. We said 50 square meters plus some open space. Because of the increased radiation, just looking at the limits you normally sort of apply of millisieverts, you say a radiologist has a maximum limit of 50 in a year. Airline crew 20. The background radiation on Earth gives you 3. On Mars, the surface radiation is 110, which is of course a lot more than Earth, but not so far off what we sometimes do allow certain professions to endure. And when you look at the average American only spends 7.6% of their time outdoor, maybe if we have some kind of a distinction between when are you exposed and when are you not exposed, of course you're going to sleep fully protected. Maybe Mars is not so undoable, and where you can say on Earth you have outdoor versus indoor, we probably have to create different kinds of gradients with more or less exposure and more or less like lines of defense against the environment. So anyway, like learning from these like different Earth vernaculars, excavation, 3D printing with local materials, and inflatable membranes would be techniques to look into. An inflatable structure is ideal for having a pressurized environment, but it offers little protection against radiation or even meteors. 3D printed structures would provide more protection, but wouldn't be as airtight. And of course, excavated structures would give you the full protection, but maybe less of a desirable habitat in terms of daylight and spaciousness. So each of the 3 techniques that you could pursue, none of them actually tick all the boxes, but if you imagine a hybrid, you can actually create an environment where you could also imagine a sort of gradient where you'll spend some of your time out in the open, some of your time within the buildings, and some of your time where you're fully protected. An interesting thing is actually water is a better shield against radiation than the regolith. You need 7 meters of regolith to be fully protected from radiation on Mars, but only 1 meter of water. So you could really imagine like beautiful ponds that are actually skylit ceilings for protected spaces underneath. Also just looking at what kind of pressure, we don't really need sea level pressure. Skylab space station has only 5 psi. So that might be something to strive for, because you have 1% of Earth atmosphere on Mars. The pressure differential is going to be quite tough on the materials. But the basic idea would be to sort of create these domes tied to the ground to use ideally robotic manufacturing to excavate and use the excavation to 3D print structures. Of course, spheres is the way to go in terms of efficiency and exposure. Different versions of spheres could create like an architecture of inflated membranes. And then, of course, also the pressure is going to be so hard on a transparent, for instance, like an ETFE membrane. So you need a technology more like this, where you have a cable net, where the transparent material is spanning the short distance, and maybe Kevlar cables are spanning the longer distance. So just, ideally you could anchor your pressurized environment into the bedrock. You can use regolith as sort of foundations, which becomes more cumbersome to build, but you can do it anywhere. By minimizing the amount of air, you also minimize the amount of pressure and uplift, so you can reduce the pull. You can also anchor your domes on regular intervals with cables, almost like inverse columns, which means that you can make much bigger environments. And finally, one thing that's quite interesting, maybe you can actually, because you have so much uplift, maybe a 1 meter thick cushion of water that, of course, would get frozen would be an amazing way to actually have a translucent, beautiful, and radiation-protecting shell around you. But of course, you need to have a lot of water to do that. So we started developing this like vocabulary of how this settlement could grow gradually, sort of from a single dome to sort of a whole environment. So, of course, even for an architect, a 100-year timeline is a little bit excessive. Dubai Future Foundation have commissioned us to make a prototype of this in the middle of the Dubai desert, in the middle of a piece of sand that actually looks like Mars, to create a facility that combines education, research, exhibition, and sort of a gardening, like focused on future space travel. So you'll have all these different elements trying to create a hub focused on developing the knowledge, the technologies, and the tools that will enable us to actually sort of go to Mars successfully, almost like a campus in the desert. This is the program we're organizing, and we are basically using the facility as a prototype. So the building itself is going to be a test. Like the part of the exhibition, if you go there, is actually to sort of enjoy the environments. These are these solid shapes that are created by the intersections between the spheres. You have different kinds of parks inside the domes. This is what it's going to look like. We're going to clear all the trees around it, so it really looks like Mars. Create these like different, almost like urban sort of layouts within. The 3D printing actually has this benefit that it's more efficient to use rounded corners. So Mars might actually look quite cozy and enjoyable. So here you see it from the outside. As you go in, you pass through streets that almost look like Arab cities, trying to maximize the protection. The light coming through the pond above you, protecting against the radiation. And you can sort of explore the different kinds of aeroponics, aquaponics that are going to be present on Mars. And maybe as one last thing, because Dubai is a little warmer than Mars, of course we have to deal with thermal heat, but it also allows us to develop a technique where we're using these inflated membranes, and by basically being able to shift a dot pattern, like sort of a positive-negative pattern, by changing the pressure, we can actually regulate the amount of light that comes in, which is also something that could be like useful eventually as a technique on Mars, but also allows you to combine something that is both a greenhouse, but can also be a lecture hall. So maybe as the last thing, we've made this like the world's fastest film where you can experience what the sort of Dubai Mars Science Center is going to look like in 3 years.
Well, Bjarke, what a great concept. I think this is great. We have a question from the audience. We have a couple of minutes for that. What applications on Earth do you believe could benefit from pursuing the development of a Mars habitat?
No, but I think no doubt. I think, for instance, 3D printing that is already beginning to revolutionize manufacturing needs to expand to a bigger scale. So like we won't be able to have formwork or factories on Mars in the beginning. So that's in 3D printing is going to be crucial for whatever like necessary replacements for products on Mars, but also for the architecture. And then I think this idea of thinking holistically in ecosystems, thinking in resources, and thinking in circular economies, like once that gets refined to the extent that will be necessary to have a self-sustained human community on Mars, then we will basically also have the solution to our challenges here on Earth.
Okay. Well, I had one comment for you from a personal standpoint. 5 psi atmosphere on Mars have to be pure oxygen for people to breathe, and you need to be careful with fire if you do that. So good luck with that. Thank you, Bjarke. It was a great presentation. Thank you for closing out our day today. Before I get Pat up here, thank you.
Thank you.
Thank you.